Good morning, everyone. Welcome to the another lecture of atomic structure. Myself, Suman Singh. So, in the last class, we have learned about the Bohr model of atom. So, from today onwards, we will learn about de Broglie wavelength, or we can say that the dual nature of matter or electron. Okay. So, when we talk about the dual nature of light, what we have seen, according to classical Maxwell wave theory of radiations, light, which is also a form of radiation, is also composed of what? Wave, okay, which spread out over a space. Again, what we have seen, what Einstein has told, that while explaining photoelectric effect with the help of Planck's quantum theory of radiation, what he says that what he assumed that light is composed of massless particle which are called photons. Okay, I hope you know this, which is called photons. What he given the name? Photons, right? Now, thus what we can say, light behave both as a wave and a particle simultaneously. Okay, in other words, what we can say, the light has a dual character. So this thing we know because we have learned in the last class in the previous lectures about Planck's quantum theory and photoelectric effect and black body radiation, like this. Okay, now we will see dual nature of matter and what is de Broglie wavelength theory. So now again we will go in the previous lecture what we have learned. From there we will take some idea. As according to Planck's quantum theory of radiation, some phenomena like photoelectric effect, black body radiations, and this black body radiations and photoelectric effect can be explained. How, when this photoelectric effect and black body radiation can be explained, if we are assuming, or if we are assuming that light behave as a material particle, right, as we have discussed earlier. So this black body radiation and photoelectric effect can be explained if light radiation is supposed to behave as a material particle. Okay, and which is localized at a particular point in a space. Now again, according to Maxwell wave theory of radiation, certain phenomena like diffraction and interference, which I have already explained in the previous lectures, this phenomenon, just like diffraction, interference, and polarization, when it can be explained when we are taking light as a wave. Okay, so we have got some ideas about this, just like photoelectric effect and black body radiation. When we can explain this, when we are taking light as a particle, or we can say that light as a particle, yes, material particle. Or when this diffraction and interference and polarization can be explained according to the Maxwell wave theory of radiation, when it is when we are taking light as a wave. Okay, so from these two from these two phenomena, or we can say that these two, by learning this all these things, we have came to know that light show dual character, right? It behave both as a material as well as wave. So now what happened in the year 1924, 1924. Okay, let's just let me change the color. In the year 1924, okay, a French physicist, de Broglie, okay, he has given he has extended, what we can say, that he has extended his idea on dual character of light to matter particle. Okay, what he has done, he has extended his idea of dual character of light to matter particle, and suggested that, what he suggested that all the particles in moving, okay, whatever the particles, if it is moving, if you are taking the example of an electron, protons, neutrons, atoms, or any molecule, okay, if it is moving, it will have dual character. Okay, what he says, he says that if any electron, if any particle just like electron, proton, okay, and neutron, or we can say that atoms or any molecules, okay, or any molecules, if it is moving, right, if it is moving, then it will have dual character. Okay, that is what we can say, that all matter particle possess a characteristics of both a material particle and as a wave. I hope you have understood what he says. So this wave, whatever the wave which is associated with that matter particle, he given the name as matter wave. Okay, I hope you have understood this. What he given the name, he has given the name as matter wave. Matter wave. So we will see what is the difference between this matter wave and the electromagnetic wave. We will see that, don't worry about this. So up to this, I hope you have understood what de Broglie has told, that whatever the material particle is there, if it is moving, it will possess dual character, and all the matter particle possess a characteristic of both material particle, both as a material particle and a wave. Okay, so now, and what if the wave associated with that matter, he given the name as matter wave. Okay, now next, the idea of this matter wave. Okay, the idea of this matter wave, he has concluded this idea, and what he says, that an electron, which is a kind of material particle, an which is an electron which is a kind of material particle, okay, has a dual character. That is, an electron, like other matter particle, behave both as a material particle and as a wave. I hope you have understood this, what he says. So we will see the equation, de Broglie equation, you can see here. So I will do here, you can. Now, how we will see this de Broglie equation, how we will derive, as we by taking the help of Planck quantum theory, or Planck's equation, we can say, or and Einstein mass energy relationship. Okay, so in Planck's quantum theory, what he says, E is equal to h mu, right? This, who has given this? Planck's. And according to Einstein mass energy relationship, what we know, E is equal to what? M c square. Okay, so now here when we are talking this, here h is what? This h is a Planck constant, this mu is a frequency, okay, frequency of radiation, this m is a mass of the photon, and c is what? Velocity of light. So what we can see, can we write like this, h mu is equal to m c square. We can write like this, I hope, because both are equal here. Now as we know that mu, in place of this mu, what we can write, h c by lambda, right? As we have learned in the previous lecture, mu is what? C by lambda. And from here what we can write, m c square. Can we write like this? So this one will be cancelled out and this one will be cancelled out. At last what we can write, lambda is equal to what? H by m c, right? We can write like this. So this equation is called de Broglie equation, where the wavelength, this lambda is called what? De Broglie wavelength. I hope you have got this. Now here h is what? This h is Planck constant. Okay, now since if this product of this mass and m and c, which is mass and speed of light, if we are considering the product of this mass and the speed of light, or speed velocity of light, if we are considering this as a momentum, because we know that momentum is what? M into v, right? This one, m into v. So this one we will learn afterward. So now, since we know that if we are taking this m and c as is, if we are calling, if we can say that this m into c is called the momentum of the moving electron, then what we can say? De Broglie wavelength, this lambda is equal to what? Planck constant, this one, divided by momentum of the electron. I hope you have got this up to this. Now here you can see they have written v, right? So I have written c, you have he has written, here it is written v. So how it is coming, I will show you now. What we have seen, according to Planck constant, E is equal to h mu, right? And according to h mu, we can write like this one, h is equal to what? C by lambda. We can write like this. I hope you are understanding this. Now again, according to again, if we are if the energy of the photon, if the energy of a photon is E, and with the mass, if it has a mass m, and and moving with the velocity c, then from the Einstein mass energy relationship we can write like this, right? E is equal to mc square, right? Mc square. Now from this equation, when we will solve, we will get what we have got previously. E is equal lambda is equal to h by mc, right? So now what we will do, if this equation, if the above equation is applied to the moving electron, if we are applying this equation to the moving electron whose mass is m, okay, if we are applying, suppose this is an electron which is moving in this direction. So if this equation, whatever the equation what we have got here, if this equation we are just we can say, if this equation we are applying on an electron which is which has a mass m, suppose this electron is mass is m and it is moving with a velocity v, okay, velocity v, then this equation how we can write? Then we can write like this, right? Lambda is equal to h by m v, right? That is why they have written here, and lambda is equal to hb here, this one you can see, right? So I hope all of you have understood. So this equation lambda is equal to h by mv is called de Broglie equation. So I hope all of you have understood this thing is written here, you can match from here, they have everything is written here. Now next is what? After that we will learn some of the terms which is not given in the notes, but we have to know these terms. What I have told you, this de Broglie, what he has given the name matter wave, right? Which wave he has given the matter wave? The wave associated with the matter particle, he called them matter wave, okay? And electromagnetic wave, we know that. So what is the difference between these two, this matter wave and electromagnetic wave? So first difference is what? De Broglie matter wave are not radiated into empty space or emitted by particles, okay? This de Broglie matter wave are not radiated into empty space or emitted by particles. What we can say, what we can say, that they never dissociated from the particle. This is about matter wave. Now, as we know about electromagnetic radiations or electromagnetic wave can be absorbed or emitted. Okay. Now next, this de Broglie matter wave travel with the speed which depend on the nature of the matter particle. Means what? Whatever the speed of this matter wave will be, speed of the matter wave the speed of the matter wave will depend on the nature of the matter. Okay, but as we know that electromagnetic wave which proceed with the speed of light. So this is the basic difference between matter wave and electromagnetic wave. Now next, two scientists named Davison and Germers. Okay, these are the they are two scientists who experimentally verifies what they have done. They have done an experiment. Okay, they have done an experiment, and through his experiment he suggested that he has proven the wave nature of electron. Okay, through his experiment he has proved the wave nature of electron. So what was the experiment? This Davison and Germer, two scientists, they produce a beam of electron. Okay, they produce a beam of electron. Suppose I will try to draw here. They have produced a beam of electron from here. Suppose the beam of electron is coming from here. Okay, they produce a beam of electron. From where he has produced the beam of electron? From an inconditioned tungsten filament. Okay, with the help of inconditioned tungsten filament he has produced a beam of electron. Okay, and after that what he has done, he has accelerated it in an electric field generated between the two grids, just like this. Here suppose from here electron is moving like this, suppose. Okay, so here he has put two slit. Okay, here he has put two slit now, and he has put here electric field. This one is negative, positive. Now accelerated between two grids. Now this beam of accelerated electrons so produced, which is produced here, you can see this is the beam of accelerated electrons which is produced here. What he has done, he has allowed that beam of electron to fall on a surface of a nickel crystal. Okay, he has put here a nickel crystal. Okay, this is a nickel crystal. He put here in a nickel crystal. So the electron, what when this electron came and that means hitted this nickel crystal, what happened then? You see, the electron get and diffracted. Okay, this electron has got diffracted from the molecular layer of the crystal. Okay, this means you can say like this electron beam has diffracted like this. Okay, since board is not there, so it is, you have to understand this diagram. I hope it will be given in your book, you can see from there. So this is diffracted like this. Okay, this is diffract after diffraction and diffraction. When it has diffracted, it was allowed after a diffraction through the molecular layer of the crystal. What they have done, they have putted here a photographic plate. Okay, they have put here photographic plate, and that allowed this beam to fall on that part photographic plate. So when this diffracted electron beam fell on that photographic plate, what they saw a luminous spot. Okay, they saw a luminous spot composed of concentric bright and dark line, which are called electron beam diffraction ring. Just like this, you can see, like this, one circular line like this has obtained here. Okay, so this circular line means you can say like this, like this, like this circular line has been obtained here. Okay, like this line. So this diffraction ring, this is called what? Electron beam of diffraction ring. Now this diffraction ring, what they have seen here, this diffraction rings given by this electron beam was found to be similar to those given by the X-ray. As we know that X-ray is what? It is a wave. So the beam which we are showing here, through this experiment, the same beam has been observed, similar beam has been observed, or we can say the similar beam is been given by the X-ray when they are diffracted by a crystal. Okay, so means what we can say, through this experiment they have understood that since X-ray is a wave, and when we are doing same experiment with X-ray, it is showing the same diffraction like this diffraction beam, and when we are using electron, then also they are showing the same thing here, just like this diffraction. So through this experiment, they concluded that this similarity between the electron beam diffraction light and those of the X-ray ring confirms that electrons are also waves. Okay, okay, I hope you have understood this experiment about the division and German experiment. So this was about the wave nature of electron, we can say like this. Now if you remember, in the when we were learning Bohr model of atom, at that time, what Bohr has told, that angular, he has told anything about, he has told something about angular momentum, right? So what he says, he has told that angular momentum mvr, what he says, is equal to nh by 2 pi. Okay, nh by 2 pi, he has given like this. If you remember, if you have seen the previous lecture, Bohr has given this equation. So now, but he has given this equation, but he was unable to explain this equation. Okay, as you can see here, I will show you. As we can see here in the demerit, limitations of Bohr model, angular momentum. About the angular momentum, you can see here, I will show you. Bohr has given angular momentum of the electron is an integral multiple of nh by 2 pi, as you can see here. Here what he says, you can see here, right? This one, Bohr has given this equation. So but he has given this equation, but he has not told anything about how it is happening or why it is happening. He has not told anything about this equation. Okay, just he has given his equation that angular momentum of the electron is nh by 2 pi, but he has not explained that one. So now we will try to explain that mvr is equal to nh by 2 pi with the de Broglie concept. Okay, so how we will explain this, we can see here what he says. Angular momentum m sorry mvr is equal to nh by 2 pi, right? This one he has given. Now next, if we are considering, if it is a particle, if electron has a particle nature, then it is all right, then this equation is all right, no need to change anything in this equation. If we are considering the electron as a wave, okay, if we are considering electron as a wave, then how it will move? Suppose this is a circle here, and how it will move, if we are considering electron as a wave, so when the wave move, it produce trough and crust, right? Like this, you all know this. When the wave is moving, it will produce like this, trough and crust. So when, if it is moving in a circular path, then it will move like this, right? It will move like this, right? So if from the place where it is starting, and if the wave is completing is entire circulation, and it is, if it is reaching in the same place, then we say that this is a constructive interference, right? I have explained you about constructive and destructive. So if it is, suppose it is like that, if it is in one go it is like this, and if in the another go it is coming like this, then it will not happen, okay? If it will not be valid for this question. So it can't explain like this. Or we can say that if it is like this, then it will show as destructive interference. So it will, we doesn't need this one. We need that, what we need such a wave which from where he is starting, and after the completing one circulation, it is reaching the same place, okay? Suppose it is reaching like this, here we can see that like this. Again, once again, let me draw this. Suppose this is a wave. If it is starting from here, it is going here, 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 like this, and it is ending in the same place, right? So this type of interference we want. This is called what? Constructive interference, okay? So what we can say from here, by looking at this diagram, what we can conclude, that the circumference, this one, the circumference, which is what we write for circumference, I hope you have learned. What is the formula? 2 pi r. Circumference, which will be equal to what? Number of waves, okay? Number of waves, suppose how many waves here? 1, 2 and 3, right? So it will depend on the number of wave, so it will be n lambda, right? I hope you have understood this. So the its circumference will be equal to n lambda, means how many wave it is generating. Here n is what? It is an integer. It will be 1, 2, 3, 4, like this, okay? 4, like this. So we can say that the circumference is equal to number of wavelength. Means what? If one wavelength, or two, one wave or two wave, if it is one, it is one, we can say that it is two, it is three, like this, okay? It will depend on the number of wavelength. So as we know that from this equation, if you arrange this equation, what we will get? Lambda is equal to what? 2 pi r by n, right? This we will get. So if we will arrange this, what we can get? Wait, sorry, okay? So what we have got here, 2 pi r is equal to n lambda, n into lambda. N is what? Here it is, n is an integer, and lambda is number of wavelength, okay? So after arranging this, if we want to arrange this, here lambda, in place of lambda, what we can write? If 2 pi r, what I have told you before starting this equation, that we will take the help of de Broglie wavelength, right? So according to de Broglie wavelength, lambda is what? H by mv, as we have proved just before. Now it is h by mv. So when we will rearrange this, we will get what? M v r, which is equal to nh by 2 pi. So I hope all of you have understood this. So this equation, mvr is equal to nh by 2 pi, was not explained by Bohr. He has just given this equation, but he has not explained why it is happening like this. So with the help of de Broglie wavelength, we have explained this. Mvr is equal to nh by 2 pi, okay? I hope all of you have understood this. So in the next lecture we will learn about this Heisenberg uncertainty principle. So till that, thank you.